This lecture is now going to go a bit deeper than we have done previously. So we had the symmetries described in lectures 3 and 4. The unbroken symmetries, as far as we can see, they're unbroken. We've not found anything that will break them. That seemed to suggest they're close to a true foundational level in physics. Also, the fact that we've been able to use the foundational methods to resolve more complex problems in physics. Things about, for example, particles, quantum mechanics, other aspects of more complex physics. We've been able to make some suggestions about those, and some of which seem to be paying off. So, if this is a valid inference, then there's only one major question left for us. To say that we have some way of starting with a foundation for physics. Does the foundations of physics have a foundation? And if so, what's it like? If there is a foundation for physics, then it also has to be a foundation for mathematics as well. Otherwise, we can't explain why we apply mathematics to physics. And maybe to a much more general aspect of information processing. We might think, from the basis of 20th century massive success in digital computing, fantastic achievement, the great technological revolution of the 20th and now the 21st century. Maybe nature is structured on an information system similar to the workings of a computer. And one would be reasonably inclined to think that. Modern computers are based on the Turing machine. Digital logic and the rewrite or production system. And this is why I've asked my colleague, formerly from the computer department, Bernard Dyers, to be with us, because I worked with Bernard on this project. So this is essentially, the rewrite or production system is essentially the basis of programming or algorithmic processes of any kind, the sort that using computers. So if you've got a computer program, you can express it in this way. And we've got a pretty clear idea of how they work. And this is a conventional rewrite system has 4 fixed components. It has an alphabet, all the things that you're going to use, all the things that you're going to investigate in it. You have rewrite rules or productions, a start axiom or symbol, and a stopping criteria. And Bernard again is the expert in this area. And this is one of his examples of how it works. For example, we can devise a process for generating Fibonacci numbers. We've got 2 rules, A goes to B, B goes to AB, and our alphabet is composed of A and B. So everything that we're going to look at is A and B. And the rules are that A goes to B, B goes to AB. We've got a starting symbol, A, and we will then follow the rules through. This n equals 0, that's the first generation, the 0th generation, symbol A. And that's the first generation and on to the 7th and on to infinity. You don't necessarily have to have all 4 criteria. For example, you can let it run forever. It doesn't have to stop. But of course, if you're doing a practical program, you would have to stop at some point. Now, rule 1, we start with A. It tells us to replace it with B. Rule 2 tells us to replace B with AB, so we write AB. And then we change B to A to B, B to AB, and so forth, and carry on. And we get bigger and bigger string created. And the important thing here is to look at the length of the string. The length of the string follows a very familiar pattern to us, that's Fibonacci numbers. So that is a production system, a rewrite system, conventional one for writing. This is my interpretation here, because the rules A to B and B to AB are those of quaternion algebra. I goes to J, J goes to IJ, which is the same as K. And if you've got a string like that, it appears to be creating a fractal-like structure in 3-dimensional space, but situated in one plane. So you're pushing 3-dimensional space into one plane. I was saying this is situated in the AB or IJ plane as in holography. So this is an interesting physical representation of that particular rewrite structure. And what to me is an interesting physical interpretation of what the meaning of Fibonacci numbers and so forth in this context. This will become a logarithmic spiral. So really, instead of coming into the third dimension, you're always forcing it into the plane, but because you're forcing it into the plane, you're forcing its extension in length. So that's an interesting interpretation. So there are, as you say, many interpretations. Now, if we had a system in which all four elements, alphabet, start object, rules and stopping criteria, could be varied, then we would have what we would call a universal system. So if we could somehow vary those within a process, so they weren't fixed at the beginning or the end, they weren't fixed at all, and that there was some way of them being varied, it would be what we would call a universal.
Totally undefined system.
Not undefined, universal. You'll see, it's not undefined. It's just not defined to be fixed.
It is undefined in fact that there is probably not an automaton that would run it, but that's another issue.
Yeah. Well, there is. We call it nature.
This is getting heavy.
Well, let's just concentrate on this because it's quite a difficult concept. So the algebraic structure, which we think lies at the foundations of physics, seems to be generated by a process of this kind. And let's see if we can do it. Possibly an information process. Can we use our concept of totality zero to find the process or the algorithm? And should we expect it to be universal if it is? No, as far as I know, there's no previous one known. And so Bernard and I set out to see if nature would supply one. And I think we got more than we bargained for. I would say we did. And see if it looked like it was driving physics and mathematics. And specifically as we already have it in this Klein-4 parameter group, the group of four, space, time, mass and charge, and the nilpotent package, an algebraic structure which we use to package the whole thing together and make it apply to physics. And it's important here that we don't assume prior knowledge of mathematics. Virtually impossible to do that because our very language is built on mathematics. We say two, doubling, and that kind of thing, and you can't avoid the language. But yet, you've got to try to avoid having prior assumptions about these things. So counting has become basis for everything we do. We learn it as children. There's one, that's two, that's three, that's four. Counting is one of the first things we learn. And in fact, we got to realise that counting is loaded. Number one is a loaded concept. It's not a simple concept. It's got a lot of stuff in it.
So this prior knowledge even includes numerical counting sequences?
That's the idea. Try to exclude the fact that we know about that. Now, we can't completely eradicate it from our language, but we can say, try to get a picture as it would be if we could. So what we're going to assume is that the universe, or any alphabet within it, always is a zero totality state, with no unique description, and so it's infinitely degenerate. In other words, it's zero, but we can't say, wow, we know what it is because it's zero, because we don't know what zero is. And we infinitely don't know what zero is. More than anything else, we don't know what zero is. So we have to continually regenerate the alphabet in such a way that it's always new, but there's no limit or stopping criteria. So the new state created is always another non-unique zero totality. Or it is unique. Whichever way you want to look at it. You can't describe it either way. I like to think of it as a zero attractor. That's a good way of thinking of a zero attractor. So we always push back to zero, whatever we do. So if we've got a zero attractor and zero deviations from zero, let's call it R. Originally we had R for real numbers, but it doesn't represent numbers, it's just something. And so there'll always be some automatic way of recovering the zero. Let's call it a conjugate, let's call it R star. So we got that, and that represents our non-unique zero totality. And that, as soon as we've written that down, we want a new structure. It's not enough, we want a new structure. Okay? It's not an easy concept, this, so we'll have to concentrate hard. And I say, when we actually work out the process, I'm going to say that we're going to get a lot from this process. We're going to find self-similarity, scale independence, duality, bifurcation, holism. Lots of things will emerge automatically from this process, we think. It will have no fixed starting or ending point, and an alphabet and production rules that are endlessly reconstructed. So this will fulfill our conditions for universality if we can do it. The self-similarity is a necessary consequence of the fact that we've not got a fixed starting point. And what it will suggest is if there are physical applications at one level, then there are likely applications at others. Maybe not just physical, maybe in any sphere. And we've noticed in the past how much self-similarity there is in nature, how much the same patterns repeat and repeat and repeat. Physics has its own version of it called the renormalization group, but it goes through the whole of nature, same patterns or similar patterns. So as we scale up from smaller to larger systems, we can imagine some principle, such as the renormalization group or some other principle, will take effect to keep the structures similar. Now, one way of making sure that the structure alphabet is new, so if we got an alphabet, we start off with 1, and then we get a new alphabet. If we incorporate the old one in the new one, then it must be new. So the new one will become what we might call a sub-alphabet of the old. So the old one will become a sub-alphabet of the new. And we'll just continue doing that indefinitely. What we're doing is, in fact, defining a series of cardinalities. It's a bit like what Cantor did with infinite numbers, only we're doing zeros. We've got cardinalities of 0, so we create a new cardinality 0, a new cardinality 0 forever and ever. So if you're the observer, let's call it somebody inside the system or something inside the system, call it universe, nature, reality, whatever you want to call it, we have to start from something which is a minimum description of 0 totality alphabet. So we have to start from that because we're inside it. But we can never get to that totality. We keep trying it and we never get there. So the successive stages are all zeros as we go from one to the next. But we ensure that the cardinalities by including the old one in the new one. So let's put something like that down. That's a new cardinality. Well, that will include that one, the old one. We can start anywhere we want, any arbitrary 0 totality alphabet. There's no natural beginning or end. And so the process is always holistic. We have to include everything. Now, we found a convenient way of doing this. It's not the only way by any means, it's just one way. But what we did was concatenate, just put things together. No algebraic significance in this. Nothing specifically algebraic in it. It may look like algebra, but it's not algebra, it's not mathematics, it's just trying to build up a picture of what may be happening in nature. So since an alphabet is defined to be a cardinality, then anything other than itself, so if you say, this is my alphabet, that's a cardinality, so it's totality 0, so it's everything. So anything from within inside that must be a sub-alphabet of that. And there isn't anything else till we build a new cardinality. And that's what cardinal means, it means everything. If we didn't have everything, then it's not a cardinality. Only concatenation of the entire alphabet will produce a new cardinality. So if I take a bit of the alphabet and try to concatenate it with the alphabet, then I will just get the alphabet. The only way to get a new one is to do it with itself, and that will create a new one. There's two aspects. We will use this symbol, though we don't look at them as big algebraic symbols. I'm just using the word symbol because I can't think of any other word, for create. If I've got an alphabet and I concatenate it, just put the terms of the alphabet and the terms of something from within it next to it, I will only get the alphabet. That will be the final result that we'll get. I'll get nothing else because I've defined this to be cardinal. Therefore, if I put something from within it, concatenated with it, I'll just get what I started with, the alphabet. So there's nothing new. That's what I call the conserve. And this, it will symbolise it. Then there'll be another one which will create the new alphabet that I have to do because my cardinality isn't the end of the story. I have to carry on creating a new one. To do that, we're going to put alphabet next to alphabet to do that. So if I put the whole alphabet and concatenate it with the whole alphabet, I say, yes, we need a new cardinality. And as Des was saying earlier, what we've got to do is make simultaneously recursive, create everything at once, and also iterative, so build up from one item at a time. So we've got to do both. It's got to be both. It will be fractal. You can see it will be fractal, and it can begin and end at any stage. And we've got to think of it as not existing in time, but existing in something timeless, and not existing in space, but existing in something spaceless. So it's a purely abstract concept. It's got to generate space and time, otherwise it isn't prior to physics. So the two aspects are simultaneous. One doesn't happen, then the other, they're simultaneous. We will only know which new alphabet will emerge when we've ensured that all possible concatenations. See, if we do that, we can only do that if we ensure that this occurs as well, all the time. And that is the key to being able to do this. To do that at all, to create the new alphabet, we've got to ensure that all these things work as well. Every way possible. And we will see how that forces our hand in creating this alphabet.
Definitions.
So if we start with a zero totality alphabet in that form, we have to assume that this is not necessarily the beginning. So that might not be the beginning. We don't know what the beginning is. So it's already, if you like, bifurcated because we've got the term and its dual of some sort. And I have to use the word dual, even though that conjures up the concept of two, even though we haven't got the concept of two. That's just our language. That's not because we've got the concept of two. We'll show where the concept of two does come from. So we have to assume we can't access it directly. So even this must have come from a zero totality, but we can't access it directly. And we might talk about this as a doubling process, even though, as I said, we haven't got the word two yet, or concept of it. Our language is limited here. We're trying to posit an ontology that exists before our observation begins. So even before our observation begins, we've got an ontology, whatever it is. Now, here's where we begin to do it in a more technical way. I've got this alphabet here. I'm now going to concatenate it with a sub-alphabet there and maybe get something like that. They're shuffling your pack of cards, if you like. Here, I'm going to concatenate it with that, and I've got to get something that's different but also the same. So that's different, but it's also the same in totality. So I can do that, that will work. And then if I do that, I can then show that I must have these rules as well. That's the conditions for those, will be those rules. And then the next stage is to show that this isn't unique and that a concatenation itself will produce a new zero totality, a new cardinality. So we'll get to the next stage. Now, of course we might think something like AA star might be the new one. But if you look at that, that's completely indistinguishable from that because we don't know what those symbols mean. So we can't just say the new alphabet's AA star, we can't do that. What we can do is say something like that because that incorporates that, so it's got to be different. But we've got to ensure that these terms are different from those. And I've numbered that equation. It's the only numbered equation in the whole talk, so we'll come back to that. So let's do all the rules that we have to do to make sure that we can do this and get something new. So if we do that one, yes, well we can do that, that's okay, that we get that. If we do that, then we've got to change everything a little bit, but overall it's the same, but locally different here, but globally it's the same if you like. Let's try this one. Yes, we can do that. That will make sense, and then globally it's the same. And then we do that one, and we can get that, which is again different and globally the same.
It's not obvious the algebraic, for want of a better word.
No, but if you sort of replace these with algebraic numbers, you'll probably realise it is, because that's what it's leading to. But well, you've got ordering, but you've got the same totality, which is what we must have. That's the key thing. Now, clearly, A and R have got to be different. So if I had R there, it would be RR, it goes to R. So AA cannot go to R, it must go to R star. Otherwise AA and RR are the same, and A and R are the same, and then we've not extended our alphabet. So to extend our alphabet, we've got to do it in such a way as our AA has not got to be the same result as RR. It's got to be a different result. Duality is intrinsic to the process. If we do an operation, that alphabet and that, the same alphabet, you get this new alphabet which is twice as big when we use language like twice, which we're not allowed to use yet. But previously, I just put that gap in there to show it's like kind of, that contains the old alphabet and then this new thing which is like the old alphabet, so it's like a kind of doubling in our way of looking at it. That's that stage, that's pretty easy. Let's try this one. let's try to extend this alphabet, and let's suppose we do the first thing we would think of, which would be something like that. And that doesn't work. The reason why it doesn't work is because it will fail by the conserve mechanism if we go through the whole process of looking at each one of these by all the sub-alphabets. We won't get the correct answer, because we will get concatenated terms come out like AB and AB star. We'll get that come out instead, and that will not work. So we can't do that. That might work, so we can try that. If I try concatenating those terms with each of the sub-alphabet, I'll get new terms which are not in the alphabet, which is no good. So I've got to make the alphabet big enough to incorporate all possible things that will emerge from doing that. And so let's try that. And let's start going through the process that we went through. Let's try all of these separately. That's okay. We just change the stars around, that's okay. The A's, we've done that before. And the new terms will look like that. They're in the alphabet, that's okay. The B terms, similar. We can get away with that, that's okay. But not when we get to those. When we get to the AB terms, when we concatenate with the AB terms, then we'll find that there's options. There's two options. If we concatenate with the AB terms, if I put AB times all that, AB star and all that, then I've got two options. Eventually, the AB terms have got to come out as R's and R stars to make this work as a pattern. We've got that option or that option. We could go to the commutative option or the anti-commutative option, as I call them. Now, if we go to the commutative option, what we find is that we haven't extended our alphabet, because our AB looks the same as R. So it's not an extension of the alphabet. So we can't do the commutative terms. The only way to extend the alphabet and fulfill all other conditions is to go to R star, which is the anti-commutative option. It's the only one that produces something new. So the labeling is arbitrary in this structure, completely arbitrary. These symbols don't mean anything, just arbitrary. So the labels A and B alone can't distinguish these terms from each other. You can only distinguish them by their outcomes. You can't distinguish them by the labels, because we've got no right to assign particular labels to these terms. So this is what this is the only option that's available to us, to use the commutative option. This means that if I do AB star, I will get R star and not R. And if I do AB, I will get R star and not R. That's the only way, in fact, we get an extended alphabet. It leaves A and B indistinguishable except by labeling, and so doesn't. So if we do this default option, then it works. However, what do we do for the next stage? Because we find we can't bring in C and we can't bring in D and extend it that way. If we try to bring in C and try and do this structure in this way, then we will find that we get inconsistencies. We can't get a consistent pattern out. It doesn't work. So, but what we can do is to say, we start again with a commutative term C, but an anti-commutative term to the C, which is D. So we get AB and anti-commutative with each other, CD anti-commutative with each other, EF anti-commutative with each other, and so on to infinity. And the key thing there is that each of these will be unique because it has a unique partner. So terms can be defined as unique by their partners because they have unique partners. So if we have A, then we know it's got a unique partner B, so we know A is unique and B is unique. If we have C, we know that's unique because it's got a unique partner D. But A and B, A and C are not partners, and B and D are not partners. Each term has a unique partner. So anti-commutativity produces a closed cycle, if you like, with the components AB and AB, their conjugates, and you can't have any further terms anti-commuting with them. But we can continue it indefinitely because each term has a unique identity because it has a unique partner. So we've got an identically structured regular series of closed anti-commutative cycles, each of which commutes with all the others. And so now we've got a system that will work for this. And we can't really think of another one that will unless we actually start introducing new ideas. And we've gone for the minimum ideas that we could. Now this structure is familiar to us because if you like, each one of these alphabets, each one of these little groups, here, it's like introducing a new symbol in binary arithmetic. You're going to the next level, to the next level, to the next level. So these become like an infinite series of finite binary integers in conventional mathematics, each alphabet representing a new integer. So we can regard the closed cycle as an infinite ordinal sequence and so establish for the first time in this process both the number 1, so we can treat them as numbers, but we can also treat them as Boolean symbols, 1s and 0s. It's the symbol 1 of classical Boolean logic. So we can say that in this way of looking at it, mathematics and digital logic become emergent properties of a rewrite process which has no specific starting point and can be reconstructed endlessly in a fractal manner. Self-similarity at all stages and a zero tractor. And we can actually construct arithmetical mathematics and digital logic by doing that. And we say it's just a pure system of process. It doesn't actually have any physical meaning, it's just pure process. And we can represent it as a series of doublings or bifurcations similar to the initial creation of that. Even when what we're saying, this, if you go to what we can use new words now to represent what we're doing, if we go to that, A and B, A is complexification, C is complexification, that's the words we could use to represent them because we're doing something new to create that new symbol. If we, going from A to B is what we might call dimensionalization. We're making it dimensional. So we have original conjugation, the zeroing process in the first alphabet, and then complexification and dimensionalization. We create a new cycle and then close the cycle. Complexification, dimensionalization. And we go to infinity to do that. And there's no reason why we should stop. We can carry on forever. We retain the old alphabet, whichever it is, and duals in every term. Now there's lots of different ways of representing this, but one that we could use is mathematical. This is only a representation, it doesn't mean this is mathematics. We can represent it, and that representation we then call mathematics. We can create a discrete integer system by applying this to the original terms, R, A, B, and so on. We can also create an entire arithmetic and an algebra. Once we've generated integers, we can do the rest of the constructible numbers. We can also consider the unconstructed numbers that define unconstructed states that we started with as being parallel to the concept of real numbers in the Cantorian sense. One of the things that's interesting about this is we only get discreteness at the point where we introduce anti-commutativity. And it seems to me that in nature there is no discreteness unless we have anti-commutativity, dimensionality. Dimensionality and discreteness are the same thing. Anti-commutativity, they're all the same concept. There's no other discrete concept in nature other than those. Specifically three-dimensionality. So it's the ultimate source of discreteness, in my opinion, in a zero totality universe. And they're the same concept. If we've got three-dimensionality, we've got discreteness. If we've got discreteness, we've got three-dimensionality. This is a symbolic way of representing the process. I want to show you what those deltas are. Those deltas are the alphabets. One mathematical representation we can do is now an algebraic one. Now we've got digital logic and binary integers, we can use an algebraic series which generates these as numerical values. This can be our first alphabet, our star. That is our A's. A star. Sorry, that's our B. So that's our A, that's our B, that's our C, that's our D, that's our E. And so on to infinity. And these things are quaternion operators. I's and J's are quaternion operators. Notice we don't need to define the K because that automatically emerges from multiplying the algebra out. And then we start a second one, then a third one, and so on, and to infinity. So at this point here, when we got these four, this is the algebra for three-dimensional space. This is the Clifford algebra of three-dimensional space. Multivariate vector algebra. This is complex algebra, this is quaternion algebra. This is double quaternion algebra. This is complex double quaternion algebra or double vector algebra. And we can construct all the bits and pieces to create those entirely in that way. So these become A, B and C, D become, this is a representation, this isn't what it is. The alphabet is prior to this is a representation. The fourth stage we have repetition, then it continues indefinitely. For example, I3 in the sixth alphabet becomes equivalent to the algebra of complex numbers. So complex numbers in this way of looking at are just part of an incomplete quaternion set. It's just one that we've not completed. So I've mentioned this before, conjugation, complexification and dimensionalization, three processes. So this is what we would get. And this is what we need. We need to get to this level to generate Dirac algebra, the algebra of the nilpotent Dirac structure. If you look at this algebra, and you do it in Clifford algebra terms, you see that that is made up of those four algebras. Those four algebras become equivalent. If you took those four algebras commutative to each other, you would get that one. So it's isomorphic to the gamma matrix of the Dirac equation. It represents the commutative combination of the first complete Clifford algebra with all its subalgebras. So that's the first complete Clifford algebra. That's a subalgebra, that's a subalgebra, that's a subalgebra. If we considered all those as commutative to each other, we would get that. So in many respects, the sixth alphabet will be a particularly significant stage in which the repetitive nature of the sequence becomes first fully established. And I say this is what we mean by a rewrite system order code. We need that to generate it. So if they're all independently true, if all the algebras are a separate representation of nature, then to put them all together and put the first four all together, we would generate the Dirac algebra in that format. And do we have that in nature? Well, I think we do. In physics, we have exactly that structure, because the first four algebras are exactly the algebras that we represent mass, time, charge, and space with. And we've seen that all their properties come from their algebraic nature. Once we've defined their algebras, we've defined those concepts. To simultaneously have those independently existing and to create a group structure which itself is a zero totality, then we need the sixth alphabet to combine them all, as I mentioned earlier, which is the Dirac algebra. We just generated these completely independently by a unique process. We don't need any numerical values to specify them. You can choose any values you want. And if we choose values in which we will always get for that sixth algebra nilpotent structure, then that's one way of getting to zero, and it's like a truncation of going to infinity. So it's a bit like when you've got commutative algebra, you can go to infinity. You've got anti-commutative algebra, you box it off in a fixed area. So we got two options. We can go to infinity with a mathematical structure. We can box it off in a particular area and get our physical structure. So we got options. So the nilpotent condition defines its conjugate as a mirror reflection of itself rather than a new state. Physically, we can call it vacuum. And I've mentioned this before. The binary 1 equals 1, 2 to complement and so forth. Minus 1 is an infinite string of ones, a vacuum of ones. And so it's not an arbitrary analogy to say that binary numbers and physics both incorporate a concept of the other being vacuum and being an infinite sort of vacuum at that. So the rewrite process is a fractal one in which alphabets are all at one level can become the units of another. So we can imagine an interpretation of this structure in which every new symbol represents the creation of a new nilpotent alphabet. I'm going to do something different now, but it's based on this. This is based on a recent paper with Peter Marsa, another colleague. And this represents entropy as a concept that recurs naturally out of it. We've thought of this for a long time, but we've been able to pin it down a lot more now. Because every alphabet always includes the previous one, it's intrinsically irreversible. Because you've got to include the previous alphabet, so you've got an irreversible process. So every new alphabet is always an extension of the last, and it provides us with the simplest definition of entropy. If you're bifurcating at each stage, you're going to get two n components at the nth stage. So if we take the standard definition of entropy, I mean, we often think of entropy as a physical concept, but it's nothing of the kind. It's just a dimensionless number. We had integral of dq over t, but that's only because we've used the chemistry of water to define temperature. It really, dq over kt is really what it is. And if you do that, then it's a dimensionless number. So this k bit is just a historical accident. What entropy is logarithm of the number of available microstates. K is only there because we've, say, historically separated temperature from energy. Now we can redefine entropy simply as, say, S prime as the number n, the order of the alphabet from any given beginning. So that's our entropy. Because the previous measure of entropy becomes kn logarithm 2, so it's just the choice of numerical factor. So if you've got equally probable microstate at the nth stage 2 to the n, that should have been 2 to the n, not 2n, previously. This gives a measure of the increasing complexification or disorder. If you're going through alphabets and doing 2 to the n over n cycles, then you'll be increasingly complexifying, disordering it. So this is true whatever the process is, whether it's quantum physics, chemistry, biology, the brain, whatever, it'll do this. Any macro system, anything will operate in this way. This is the general process.
Are you saying that that's the second law of thermodynamics?
Basically, yes. It's more than that, by the way. It's more interesting.
I realise that, but that's how we...
Yeah. Entropy always increases in that experience. We can use this as evidence that the rewrite system is always bifurcating. So the fact that entropy exists and always increases tells us that we're actually bifurcating all the time. The rate of entropy increase where we measure the bifurcation that actually occurs, and therefore in its way it's standard plot. We can see how the rewrite process operates in any given system. We can establish it's a universal process. Shannon had a view of 1948 that at least kt logarithm 2 must be transmitted per bit of information. And of course, digital logic and information in a computational sense is simply a special case of what we are talking about. So we can see why that would work. So if the energy in the message is indeed dissipated, then it's minimum dissipation and information measure. Now, self-organization allows us to take this loss as a measure simply of the loss, but of the information which enables this self-organization to proceed accordingly. And so we can treat the self-organization as if it's a complete binary tree of ordinal measure and as a natural canonical power series structure. At some stage, the measure of information transfer and entry is determined directly by the level of the alphabet reached in some way. So we can always say, where are we in the alphabet? Well, it depends on the entropy. It shows up in the radiation forms case because it's summation over linearly independent wave phenomena phase across the entire universe. So we would expect our global scaling constants to be genuinely global. Now, the information in nilpotent quantum mechanics isn't lost, it's rather accumulated to make the global process irreversible. So what you're doing is passing from non-local indistinguishable to local distinguishable. That's the process that you're doing. And you would expect time asymmetry in transferring from non-local to local because the local always requires asymmetric time-like solutions and therefore irreversible ones. The non-local doesn't. And all non-local processes have local manifestations. We've seen that before. And this seems to be how the time component of vacuum actually manifests itself in local effects. Okay, observability, of course, is indication of events in the present. The future is still part of the unobservable, the non-local vacuum. Now, this is all especially true of biological systems, which are very highly organized and composed of many interconnecting parts. So, if you've got a bifurcation process, a manifestation of the universal rewrite system, we can say the rate at which it happens must be proportional to the free energy involved. So the higher energy, the higher the rate of bifurcation events because we've got more interconnections. The more free energy you use, the more interconnections. The more interconnections, the higher the rate of bifurcation. And if you've got a near chaotic system, that will be highly nonlinear and therefore highly interconnected. Nonlinear means more interconnected. So transfer energy at near maximum efficiency, so bifurcate rapidly. So you get a large measure of entropy in near chaotic systems. And as was said in Peter Wakeman's lecture a couple of days ago, how Stuart Kaufman has said that biological systems operate near the edge of chaos. So we get rapid information transfer in states of high entropy strongly correlated. And again, it acts as a clock. I'm saying that if we say all natural systems are entropic and irreversible in time, that's in fact evidence that they are operating according to something like our universal rewrite process. The growth of a chaotic system provides a nice parallel with this, because in a typical situation leading to chaos, say the growth of an animal population or something, you get a point where the growth rate increases above a certain value, and the equation actually produces a real bifurcation between two possible outcomes. Then the further increases bifurcates the bifurcations. And the frequency is determined by a single scale factor to preserve self-similarity. Now I don't know the reason for this number. Someday somebody will find out. Feigenbaum doesn't either. So nobody knows the reason for that particular number, but there is some characteristic number at which that occurs. So we can see that as a characteristic extension of the alphabet by a new one, exactly as we've done in that universal rewrite. You've got to look at it as process rather than bifurcation in system. It's a bifurcation in the process. So a near chaotic system will become subject to a particularly rapid change because of it's got lots of non-linearity, lots of interconnectedness. The more interconnected it is, the more it will happen. And the bifurcation will occur at the whole level of the whole system. So if everything's interconnected, the whole system's going to bifurcate more than it would do if it was all different parts, and a little bit might bifurcate and that. So when the process appears collectively, the expected rewrite leads to a complete bifurcation, a complete doubling of the options. And this is what happens in a chaotic system. Another aspect of this is the growth of complexity in natural systems. In principle, nature, our rewrite structure based on zero totality and based on nilpotent structure suggests that essentially a system, whatever it is, wants to annihilate itself with the rest of the universe. That's its modus operandi. That's what it's trying to do. It wants to self-annihilate with the universal vacuum. Everything in nature is actually striving towards this end all the time. And what it does is, well, I can't annihilate with the rest of the universe, but I can combine with this other local system. So that's what happens when fermion and antifermion connect. So the result is complexity, where the symmetry is imperfect or broken, where the parts continually strive to make further connections. So it creates a connection, but it's not totally happy with that. So your hydrogen atom becomes a hydrogen molecule. The hydrogen molecule gets combined in a bigger structure, and so forth. So the nearest you can get to stability is when an object has an environment which acts as a bit like a vacuum. So the environment creates itself as a kind of vacuum. It's not the total vacuum, but it's a sort of pseudo vacuum. So you've got nucleus in an atom, bulk molecule in condensed matter, cell in an organism, and maybe when an aerobic bacterium is absorbed with an archaeum, maybe that's what we're looking at. It's looking for an environment which is something like what it thinks the rest of the universe is. So to do this requires a maximal number of connections. It wants to do that, and that's the best it can do, and so it wants to make the maximal connections it can all the time. And so it's going to maximally generate entropy. The most desired state is the combination and so annihilation of any system with a universal background. Then the tendency of the evolution of the universe will always be in the direction of maximum entropy, because it will want to make as many connections as it can so it can do its... So that's an interesting way of looking at entropy, and it comes direct out of our rewrite structure. We've got duality in everything, because you can't get something from nothing without it. That's something and nothing only coexist if you've got duality. That's what it means. And the duality is the fermion and the rest of the universe, or the equivalent at a higher level in the rest of the universe, whatever. And everything always acts in that way. The ultimate we want to describe is nothing, and we can only ever observe something as part of a dual pair. We use the simplest symmetry group we can, which is the C2 group. If we look at physics, we see that's everywhere in physics, this duality. Factor 2, factor half, everywhere in physics. It doesn't have to be equal status. The fermion and the rest of the universe aren't equal status, but they're completely dual. 1 and minus 1 aren't completely dual they're completely dual, but they're not the same status in binary mathematics. But they're completely dual. They each cancel. And you will always get chirality as well, because this is chirality in play. When you say it's dual, but it's not equal status, chiral. And it's not a single operation, and you can keep indefinitely creating duals. So whatever we do, we will always create duals, and we can consider our rewrite process as creating duals. In the parameter group in physics, we get 3 duals, and I've used this color coding to help to understand it: conserved, non-conserved, imaginary, real, commutative, anti-commutative. There's lots of examples of these. You can read them up for yourself, but there's a whole chapter on this in 0 to Infinity, and I've written several papers on it. Action and reaction, absorb. All these are typical dual processes where you get factor 2. Bosons, fermions, electric and magnetic fields, space-like, time-like, all these things are typical dualities. Another type of duality, fermion and environment, Aronoff-Bohm effect, Berry phase, Yarn-Teller, all that sort of thing. Waves versus particles, Heisenberg, Schrödinger, the harmonic oscillating, they're all the same, they're all factor 2 everywhere. Everywhere. And you can actually put them all in a nice big table. Let's do them like that. But that doesn't exhaust them. You can include all kinds of things: Hawking radiation, whatever, Josephson effect. Everything is got this factor 2 in. And this is I think that's virial theorem, and action and reaction. There we go. Action and reaction, absorption and emission, virial theorem, object and environment, relativity, commutation relations, continuity and discontinuity, all this factor 2. Now this seems to work in one direction. So for example, if you've got constant terms, you get twice the changing terms. So that's the changing and non-changing. Real terms tend to be twice the imaginary. Discrete are twice the continuous. But actually, what usually happens is if you look at the problem one way, you get factor 2. If you look at the problem the other way, you get factor half. It's really quite interesting to track them down. But everywhere you get factor 2 or half, even squared often, it's that. So I won't go into the detail now. This is a nice entertainment for you. This is a nice bit of mathematical entertainment. This wonderful equation, e to the I pi equals -1. Now I got this because a student once asked me, are e and pi transcendental numbers in the same way? I said, oh no, they're not. They're not transcendental for the same reason. E is transcendental because it's defined by differentiation. dE by dx equals dx, e to the x. And so it's defined by differentiation. So that's the non-conservation property. I, of course, is imaginary. Pi is defined by three-dimensionality. Circle, sphere. So these three are acting to produce a collective dual to the positive unit 1, -1. And you can see there that the E, I think I may have something, no. If you take mass as the basic unit, and mass is conserved, real and non-dimensional, then let's take something that's not conserved, and then we get E. Let's take something that's not real, and we get I. And let's take something that's not non-dimensional, we get pi. Bung them together, and we get the opposite. And we can even relate this to CPT in physics, because those three properties are the other things other than mass that exist in physics, charge, space, and time. And you can pin those down to what each one of those three dualities as opposed to mass. So that's a nice bit of entertainment, but I also think it's true.
Good.
It doesn't have to be not true just because it's entertaining. And I just mentioned briefly about three-dimensionality. But we've generated three-dimensionality from the way we've derived this rewrite structure. And It's got its origin in anti-commutativity, and we think it's antecedent to number. So it's more important than number. Geometry, algebra come before arithmetic. It seems to be responsible for all the discreteness in physical systems, quantization, symmetry breaking between the forces, lots of things. So we've got 3 dimensions of space, 3 non-gravitational interactions, 3 fundamental symmetries seep into it, 3 conserved dynamical quantities, those, 3 quarks of baryon, 3 generations of fermions, endless. And we can relate them all to the same structures, the same lots of 3-dimensionality. And I don't think any other dimensionality is fundamental, not even 4 dimensions, because 4 dimensions is really 2 lots of 3 dimensions, leaving out the 5th term. You get 5 terms, as we've seen from our previous mathematics. We'll leave that, because we haven't got time to do that now. Just very briefly mention. Yeah, I'll just show you a table of various 3-dimensional things. So here's some nice lots of plotting out 3 lots of dimensions and showing how they all map onto each other. And I'll leave you to look over that later. So physics uses lots of groups, geometries, algebras, and symmetries. So does biology, as I'm finding out with my biological colleague Vanessa Hill, and we're doing extensive work in that. So does computing, as we were talking about with the rewrite structure. So we think also does chemistry and other aspects of physics. And essentially, the numbers that are most important in this regard are 2, 3, and 5. 2 because of duality, 3 because of anti-commutativity, 5 because of broken symmetry, putting 2 lots of 3-dimensionality together. So what we're really looking at, I think, when we talk about the universal rewrite system, is a general description of process, and it should apply to all these domains and all self-organizing systems. We are now investigating many of these areas, and we are in fact finding that this is very much the case. That big-scale systems of various kinds, including quite a lot of biological ones, are following these rules and giving us special insights which we wouldn't have otherwise. We find particular characteristics of this self-organization: double 3-dimensionality, 5-fold broken symmetry, geometric phase, that's periphase and things of that kind, uniqueness of objects, unique birth order, irreversibility, dissipation, chirality, harmonic oscillator, Zitterbewegung, fractality, dimension 2, holographic principle, quantum holography. All those things seem to come out in many of these systems. So this turns out to be a very interesting general concept. It's generic, and in my view, the best ideas are always generic and not specifically model dependent. And in biology, it seems, and Paul Davies, a well-known science writer, was talking about this recently, but we've known it for a long while, that some sort of information process is a bigger driver than the actual chemistry. So, okay, people think you put the chemistry together and you get biology. You don't. It's the information process which drives it, and it just plucks out the chemistry as it needs it. And we've known that for a long time. I hope that this series of lectures on foundations has given us a very different idea of what it might be about than we might have had at the beginning. It's a very different subject from anything we might have imagined. But it's got its own methodology, its own philosophy, and even its own mathematics. And it requires much more inductive thinking, much more, I don't use the word speculation because I don't think it's speculation. You've got to do a collective understanding of a lot of things at once, rather than you've got to do it recursively rather than iteratively to a large extent. It's a recursive method. Like Newton did. I've studied Newton a lot recently, and I've found that he is very much a recursive thinker. That's why he gets so many great ideas. But it is also rigorous, and we get mathematically and experimentally testable results, some of which have been tested, and I've mentioned a few, especially in Lecture 8. It also adds significantly to physics worked out at a greater degree of complexity. We're not going to ignore that physics, we're going to use it, but we're going to enhance it because we can add to it. And we have often in this lecture series used physics from that area and seen how we can enhance it, or attempt to enhance it. So its methods and symmetries can suggest answers where you can't get any others by any other means. And sometimes you can resolve anomalies which were previously very confusing and no idea how to solve them. So I would like to think that anyone who's followed this series of lectures will see that the possibilities of open drop are almost limitless, just like the universal rewrite system. It's limitless, with many opportunities for significant research. Okay, and that's it. Thank you very much. Now, repeat what I did in the first lecture. A long-term research project, many decades. There's a book called Zero to Infinity. There's even a few things in this that aren't in the book. And here I want to mention various people I've collaborated with on various projects. John Bernard is with us, Peter Martyr, who mentioned, Brian Coberline and Vanessa Hill, who have also mentioned. And most of those collaborations are still going on. And as I mentioned before, I'm very grateful to members of the physics department, especially to John and Mike for their support and help in creating this lecture series. And also, thanks very much to Dave and Christian for doing their recordings of this, their expert recordings of this series. And everybody else who's contributed, loaning me various items of equipment and so forth. Thank you very much.
Zero is part of this numerical sequence that we have prior knowledge of.
No, zero isn't part of the numerical sequence.
Right, yeah, that's what I wanted.
That never was.
Right.
It's a fundamental concept.
In zero totality, even the concept of zero
Yeah.
can't exist.
Yeah, you can't imagine it. You can't begin to think what it is.
There's no symbol for it.
No.
No.
It's important to note that 1 is in fact an infinite series of zeros followed by 1.
Well, you could do it either way. You could actually do the. You can switch around the vacuum and the particle state in physics. So what you're saying is that that is a correct analogy.
And the important thing is you need the 1 and the infinite series of 1s to
Yes.
get your 0.
Yes.
Because if you think of adding 1 with an infinite series of zeros, sorry, I should do it 1 with an infinite series of zeros, and your 1 like that, then adding 1 to 1 gives you 1, 0, 0 in the result. Continue to infinity, you get your 0.
I think of it like dominoes. You're not the first one over and the rest
Yeah.
fall.
But it's infinity. I mean, you're playing with infinity.
Yes.
That's the secret. You're not playing with 1s or 0s.
But unless you treat it as an infinite process of zeroing,
Yes.
then you can't do it.
Yes.
That's the bottom line.
Can I just make a point that when we use that two's complement concept,
Yeah.
we do actually end up with a carry bit that we have to throw away somewhere, is it?
No, it goes to infinity, so we
It
don't.
goes to infinity.
Yeah, but when you do it infinitely, you don't.
That's a tricky one, that.
When you do it in 16 bits, you do.
When you're doing 16 bits, you do. Yeah, I understand that. When you do it in a practical situation, you
Yeah,
do.
but it's also a very, very neat way of seeing what infinity can be for. See the terms in which infinity can be even contemplated, possibly, full stop.
But you've got to include it in every single
Yes.
step
Yes.
and stage, and that's the problem. That the square root of -1 gives you that wonderful capability that there are an infinite possible
Yes.
interpretations of it. So you have infinity built in by just simply including that.
Yeah, we actually developed about half a dozen, 8 papers or something. We had about half a dozen or 8 papers on all this stuff
Yeah.
over a period of time.
Yes.
Yeah.
So the Big Bang is a fluctuation, and it's striving to get rid of itself.
If you put it in those terms, yes. I prefer to keep cosmology out of it, but if looking at the universe as it is now, that's what it's trying to do.
Well, I was thinking of the Big Bang, I was romanticising. What I mean is a
Yeah.
quantum fluctuation.
Well, if one were putting it in those terms, that would be the correct way of doing it.
Sorry, just for a quick point. E is defined by differentiation,
Yeah.
not concern.
Yeah, you do d e to the x over dx equals e to the x. So you find that
So different.
number at which that will work, and you need differentiation or integration to find that number, and differentiation is an aspect of non-conservation. So that's the duality that's lurking behind that.
What does Einstein say about that?
About 4 dimensions.
Yes. How does he react to what you say?
How would he react? Well, he's not heard what I have to say. Because time is irreversible. You see. I can't go against what I've already done, the second or thermodynamics. No, seriously. I think it's okay, because what Einstein does is have 4 dimensions in a restricted domain. When you take the scalar product in and you leave out the proper time element. So I don't think there's a problem. There are 4 dimensions when you do that. So you get a 4-dimensional object when you do that, but it comes from 2 lots of 3 dimensions. It's not like something on high 4 dimensions. It's a broken symmetry, and it comes from 2 lots of 3 dimensions.